Okay, so maybe I'll just give a brief introduction, Simone, for the benefit of people in the room. I think everyone probably knows you, but so Simone was here as an INVOGE exchange student last year and worked on some data collected from Pacaya. And I don't have a long story to tell, but I just want to say that I was really impressed with how he just kept trying one thing after another. Simone was really interested in trying to get a 3D model for Pacaya using surface waves, and he tried just about everything either of us could think of, and none of them worked perfectly well, but we learned a lot, and I think he's got some interesting results that will prove to be useful as we move forward, and will be useful to other people who are doing similar things. So with that, I'll let you get going.
Okay, so thank you, Greg, for the introduction. Hello to everyone. So today I would like to show my work about the comparison of ambient noise methods to find surface wave dispersion curves at Pacaya volcano in Guatemala. So here what I want to do today is a brief geology of Pacaya volcano. So the data acquisition, so the theory about the ambient noise, so is the title of my thesis, and then some results, and obviously the conclusion at the end. So about the geology of Pacaya, so Pacaya volcano is a 2,500 meter size stratovolcano located about 30 kilometers south of Guatemala City. So it's one of the most active volcanoes in the Central American volcanic front that is the result of the subduction of the Cocos Plate beneath the Caribbean Plate. So Pacaya volcano is a complex, so it includes the new composite stratovolcano, so the old Pacaya and what we call the new mechanic cone, and then Cerro Grande, Cerro Chino, and Cerro Chiquito Scoredome. So the history of Pacaya, the complex of Pacaya, is not still clear, but some authors can recognize at least 4 eruptive phases. So the first phase is the growth of the ancestral andesite stratovolcano. The second phase is the building of the Cerro Grande and the Cerro Chiquito domes. The third phase is the building of the old Pacaya stratovolcano. So that's important. That's the important phase, the most important phase that we'll show. And then there was a sector collapse of the southwest side of the volcano that leaving a scar that is visible nowadays too. And then there was the building of the Cerro Chino, scoria cone. And the last phase is the building of the modern mechanical after the eruption of 1961. So it's the current active phase of Pacaya. So I wanted to talk about few minutes about the structural setting that for me is very interesting of Pacaya. So geodynamics tell us that we are in a compressive regime, so because there is a subduction, but regionally the study area is very complex. So the study area is south of the Polo Chic and Montagua and the St. Augustine left lateral transtensional strike-slip fault. And so this fault is transtensional, so that means that we have not only strike-slip component, but also extension component that is estimated by some authors about 8 millimeters per year. So it's a very good extension for this area. And this extension had the formation of many graben in this area, including the Guatemala City graben. And moreover, this area is split by the Yalpatagua, the bilateral strike-slip fault, the Yalpatagua fault zone. And Pacaya more probably is located at the intersection of these two, of the Guatemala City graben and the Yalpatagua fault zone. So that's important. So there is a main hypothesis made by Schaffer in 2013, that is the volcanic rift zone of Pacaya is parallel to the Yalpatagua fault zone. So it's almost a northwest-southeast trending. And this is important because what is a volcanic rift zone? Firstly, so a volcanic rift zone is a weakness zone where magma is more prone to ascent. So it's influenced by regional and volcanic stresses, and usually is parallel to the maximum horizontal stress and is perpendicular to the regional sigma 3, so it's the minimum regional stress. And collapses are parallel to the volcanic sigma 3, so that's important. We have many evidence for this hypothesis, so the alignment of the northwest and southeast trending for the historical and recent events. aligned in this direction. And then there was an important sector collapse between 0.6 and 1.5 thousand years ago, oriented in the southwest flank. So that's important. And then the other last work about Schaffer in 2016, she discovered that there was a co-eruptive landslide of about 3 meters displacement during the May 2010 eruption only in the southwest flank. So that's important. So for the data acquisition in January 2015, so we deployed a seismic array of 19 short-period 3-component seismometers around the Pacaya vent, and with distances between 300 meters to 2.5 kilometers. So some stations were located in the outside the scarp of the sector collapse, so what we call in whole Pacaya the edifice, and some of them were located in the new mechanic cone. So that's a key thing that in the result will show that this distinction. So about the theory of ambient noise, my title involves the comparison between ambient noise methods to find surface waves. So what is ambient noise? So the ambient noise is any part of the seismogram that we are not interested. So for example, if we focus on the first P arrival of earthquake, for example, the signal is the first arrival of the P, or the P first arrival, and everything else is like noise. So you can understand that this definition is like subjective, so it depends on what I'm interested to see in a seismogram. So the important thing is that the most noise is composed by surface wave, and we use this concept to construct my work. So the sources of ambient noise could be either anthropogenic, so the noise coming from cars, trucks, AC power, internet, wireless, or natural. For example, tides, temperature changes, lightning, or ocean waves. So the frequency range that we put here is like rough limits, so are not very the exact range of the frequency for anthropogenic and unnatural noise. So the important thing is that if we want to analyze a signal, so we need to turn that noise into signal. So that's important, that we use the idea of hierarchy and representative of Weber in 2007. So, but firstly, I want to introduce two important concepts that we use in the idea. So the first is the cross correlation concept. The cross correlation is a measure of a similarity between two waveforms recorded to a different station. So it's a similarity between two seismograms recorded to different stations. And what is a seismogram? The seismogram that we record from a station is like the convolution, or simply the product in the frequency domain between the source, so the source of the signal, and the instrument response, so it depends on what instrument we use, and the earth response, so what we call the green function. That's important, is the path effects of the seismogram. So keeping in mind this concept, we can elaborate this idea. So the cross correlation of a random isotropic wave field recorded by two different stations, by two different receivers, differs only by an amplitude factor from the green function between the two stations. So what does this phrase mean? So it means that if we have, for example, if we have a random isotropic wave field that represented with the black arrows in this way, so random because it's a random distribution of this array, and isotropic because the length of single ray are almost the same. So if we have this random isotropic wave field, occasionally array that is represented with the red arrow is passed through both detectors. That means that it's like that array is going from one station and is going to the other station. So it's recorded from both stations. If we do the cross correlation between the waveform recorded by two different stations, we have a spike. We have this signal of the red arrow is correlated. So in this case, for example, you can see in the cross correlation in the upper panel, you can see that there is a signal. So there is a spike in the cross correlation. That's the key thing. So keep in mind this concept and this sketch of Weber because it's important and we use in different ways. So to isolate noise in a seismogram, we can use two different approaches. So one is called the Benson et al. Analysis, and one is the spark. introduced by Aki, but we'll show in the next slides. So to isolate noise in a seismograph, you can use the Benson analysis. They are composed by different steps. So the first two are the normalization in the time and the frequency domain, what we call the spectral whitening in the frequency domain. Then there is the cross correlation per hour and per day, and then there is the stack. So the stack is simple, the sum, the mean between the cross correlation per single hour or per single day is the stack, is the sum. So to increase the signal to noise ratio. So to increase the signal of the red arrow that you see in the weather sketch. So, and the last phase is the estimation of the group and phase surface wave dispersion curve. So dispersion curve is a relation between the frequency and the velocity of the surface waves. So the distinction between group and phase velocity is that the phase velocity is the velocity of a single wave characterized by a single frequency, while the group velocity is like the velocity of a bunch of waves characterized by different frequencies. So you use both the group and the phase dispersion curve in our work. So this method, this approach requires months or years of data. So it requires a lot of data. We have only 7 days of data, because if we do the cross correlation, we need the entire day to do the cross correlation. And then requires interstation distances, so distances between two stations greater than 2-3 wavelengths. So, and then we have instead only interstation distances smaller than 2 wavelengths. So that's the key thing. So the reason why we need a lot of days of data, with months or years of data, is that increasing the number of days of data increases the signal to noise ratio. So increase the signal that the cross correlation, that the array, that ray that you see that you saw in the weather sketch is correlated. So in the cross correlation there is a spike. Intersection distance because we need to large distances between two stations, because we are sure that we focus our attention only in the surface waves, because we can expect that close to the Pacaya event, so close to an active source, we have different type of waves. We don't have only surface waves, so we need to large distances between the stations. So in our case, it's completely the opposite. So you can see that we have low SNR, low signal to noise ratio, and that's a problem for us. So the normalization is composed in the normalization in time domain, and we use 1 bit, and the frequency domain we use the spectral whitening. So you can see, for example, in the first panel, so in the panel A, you can see our raw data. So these data are only corrected by the instrument response, while in the D figure you can see our result. So we can see that the result after the normalization. So you can see that we don't have earthquake, we don't have events anymore. We are only noise. So the normalization means that that removing all type of events. So to focus our attention only on the noise. So for the cross correlation, you use for example, in the panel A, there is the cross correlation per hours, for example, in a day, so 24 hours per day. And in the panel A, you can see the cross correlation only per day. So we have, in this case, only 5 days for this cross correlation between station 7 and station 15. So in the background, you can see the cross correlation view so from the top. So you can see that the yellow line represents the spike in the cross correlation, while in the black solid line you can see the stack for the entire day. So this is the cross correlation for the entire day. For example, in this case, was January 17. In the panel B, you can see the same thing, but the cross correlation are made for the days, and the stack means that the stack of all days that we have. So these are the example, for example, between station 7 and station 15. So, and the last phase of this method is the estimation of the group phase velocities, dispersion curve. So it's like the relation between the frequency and the velocity of this wave. So we can use the definition of velocity. So simple, the relation between distance and time. So you can see, for example, in the panel A is the cross correlation, is the spike of the cross correlation divided by frequency. So you can come back and you can see, for example, in the panel B, you can see the stack. So to calculate the velocity, we can filter this stack for different frequencies, and the yellow line represents the spike of the cross correlation for different frequencies. So we have the distance between the two stations, and we have the time, because you can see that in the y-axis is representing the time. So we can estimate the group velocity, and it's represented in the panel B. So the other approach is the SPAC, what we call spatial autocorrelation method, was introduced by Aki in 1957, and is based essentially on two assumptions of the wave field. So the wave field is stochastic, isotropic, and stationary in both time and space, and it consists of dispersive surface waves. So, but what does this stochastic, isotropic, stationary, and dispersive mean? So they means that stochastic means that it's a random distribution, like you have seen in the Weber sketch. So isotropic means that we have, for example, the velocity is the same regardless of orientation. So we have the same velocity in all orientation. It's not a problem of orientation. So, and stationary means that there is no variation of, for example, in velocity in both time and space. So the velocity doesn't depend on time and doesn't depend on where we are. And dispersion is a very key concept. So keep in mind this concept, dispersion. So surface waves are dispersed. That means that waves with different frequencies travel with different velocities. So we can build the dispersion curve in this case. So this is the relation between the frequency and the velocity of the surface wave. So if we do these two assumptions, Aki relates the result of our cross correlation with a Bessel function. What's argument is simply the ratio between the frequency, the distance between stations, and the phase dispersion curve. So, but what is a Bessel function? So you can see in this figure. Don't look at the gray lines, because I explain you in the next slide. But you can see that the pattern is like a Bessel function. So where in the Bessel function is a relation between the correlation coefficient. So in the cross correlation, we have a correlation of two waveforms recorded by two different stations. So if the correlation is 1, so these waveforms are in phase. So instead, if we have -1, this waveform are out of phase. So this SPAC, usually the SPAC was developed by Ferrazzini and other authors and applied in a volcanic environment into small aperture seismic arrays. So small aperture means that the distance between stations are small, so up to 500-600 meters. And so this method is based on the selection of 10-15 time windows between the station with the same distances. So the key concept is that if we have a smaller aperture array, we have stations with the same distances between them. And the result will be like a shallow 1D velocity model beneath the entire array. So we don't have small aperture seismic array in 2015, and we have stations with far away more than 500-600 meters. So we decided to do the cross correlation between a single pair of stations. So every single pair of stations we do cross correlation. But our problem was that we have only a few days of data. So the signal to noise ratio was small. So we decided to overcome this problem to select hundreds of time windows to do the cross correlation. It's like having like a month or years of data is the same, because if we have hundreds of time windows and do the cross correlation and they start, we improve the signal to noise ratio. So the result would be the 1D velocity model beneath the single pair of stations. So we can build just a sort of 2, 3, and 3D velocity model of the entire volcano if we sum all of 1D velocity model for each station. So we modify this part. So in the figure you can see in the right panel, you can see that the gray line represents a single cross correlation of the 139 time windows. So, and the black solid line represents the stack. So simply the mean, the sum of the whole cross correlation. And you can see that it's similar to a Bessel function, like the Aki formula and the Aki idea. So the the velocity can be estimated with using the second definition of velocity. Is not simply the ratio between distance and time, but is the product between the frequency and the wavelength. To calculate, to estimate the wavelength, that in this case is our problem, Aki and Ferrazzini suggest that we can use this. The wavelength is simply the product between the distance between two stations by times 4 divided by n, where n is the number of zero crossing maxima and minima of our cross correlation. So you can see, so this idea, the concept idea that is behind this formula is that we can compare our result of cross correlation as a wave with the wavelength equals to the distance between the two stations that we analyzed. So if we have this wave, the wave is going from 1 is going to down. So at 1/4 of our wavelength, we have zero crossing. At half of a wavelength, we have only a minima, and then in the 3/4 we have another zero crossing, and at 1 wavelength we have a maximum. So that's important. So you can see that we have a lot of points in the left panel. You can see that these points are the estimation of the phase velocity for that different frequencies and for the frequencies of the zero crossing maxima and minima that I explained. So, and then we fit this point with a power law equation. And you can see it in the right figure. You can see that the black dashed line represent the Bessel function, the calculated Bessel function of this fit, or the fit of the figure A. So we use another method that is called Henney, and another method that is the evolution of the Ekstrom method. So these two methods are almost the same. Usually are made in the frequency domain. We try to use them in the time domain, like we use the spark. And so Ekstrom use the vertical cross correlation, while the Henney method is an improvement. So use not only the vertical cross correlation, I use also the vertical radial and the radial vertical cross correlations. So because Rayleigh surface waves propagate not only in the vertical component but also in the radial components. So to estimate, for example, the phase velocity in this case is simply the product between the frequency, the distance between stations, and divided by the number of zero crossing of the Bessel function of the zero order or the first order, if we have the vertical radial or the radial vertical cross correlation. I'll show you a figure. So these two methods have advantages that can be applied where distances between stations are smaller than 1 wavelength. So in our case, it's the same. And then if you use the Henney method, we have more phase velocity values to fit. So the problems are that our assumption that the 3 cross correlation look like a Bessel function. So that's the key idea. So that's our assumption that we do. And so to correct them, we use but there are some problems. There are the missed or extra zero crossing. So the correction by this missed or extra zero crossing is subject. It's not completely objective. I'll show you what is missed extra zero crossing. So for example, in this example, in the left panel, you can see respectively the cross correlation of the vertical the vertical radial, and the radial vertical cross correlation. So the vertical cross correlation, it looks like a Bessel function of zero order, while the vertical radial and the radial vertical cross correlation looks like a Bessel function of the first order. So it starts from 0. So this method is the same, is the calculation of instead of the maximum meaning of the spark, you oscillate zero crossing of our cross correlation. And we estimate the phase velocity with the formula represented above. So you can see that, for example, in the vertical and the vertical radial cross correlation, we don't correct by the missed extra zero crossing. While in the radial vertical cross correlation, we correct by 1 missed zero crossing. So you can see that, for example, in this case, you can see my mouse. Okay, you can see, for example, here that the stack of our cross correlation doesn't touch the zero line up to 1.5 Hertz. So we can imagine that there is a missed zero crossing in this point, so around 0.6. So we correct by 1 missed zero crossing. But some of you can say, okay, Simo, for me there is just true. There are no missing zero crossings, so you can understand that this approach is not completely objective. So we use another method that called Menck-Engine method. It's a very complex method and it's divided in 2 steps. So the first step is the grid search for the gas that we use in the second step. So the second step is like a refinement of our dispersion curve using an inverse problem. So I don't want to enter in detail in this method. I wanted to say just a few concepts that I want to say is like the distinction between a forward model and an inverse model. So the forward model, you start from the theory of, for example, the theory of seismology, the theory of seismicity to build the seismogram. So, for example, if we know the source, if we know the path, if we know the path effects, if we know almost everything, we can build a seismogram. It's like a synthetic seismogram. In the inverse problem is the opposite. So we start from our seismogram recorded by a station or 2 different stations, and through mathematical tools we can construct, we can characterize the medium. So we can say we can build the velocity structure or the path. We can build a lot of things. So we use just the grid source, so the just first step, because the second step was more difficult and our solution didn't converge for another solution. So the first step, so the grid search is composing of defining of 3 nodes. So at each node we can specify the number of values that each node can take, and then we interpolate with a linear interpolation of these nodes that we choose, and then there is the last step is the grid search. So it's like a iteration to find the best phase dispersion curve based on the nodes that we choose. So for example, in the right panel, you can say the comparison between the Ekstrom method is represented with this dot, and the estimation using the Menck-Engine method. So using 3 nodes. The first node is around 0.5, the second node is around 1 Earth, and as the third nodes we choose 3 Earths. So, and you can see that our calculated Bessel function is similar to the observed one. So it's similar to our result of the cross correlation. You can see in the left panel. So this method I think is the best method that we use. So is the perfect fitting between the calculated Bessel function and the result of cross correlation. But the problem is that our dispersion curve is not smooth. It's like only a linear interpolation. So I wanna say something about the result and our discussion of our results. So regarding the Bessel et al. Approach, we try to divide the cross correlation of the station outside the scarp, so in what we call the old Pacaya, and the station were located in the new mechanicum. So, and you can see we can do 2 different results. So in the left panels, you can see the result of our dispersion curve. So for old Pacaya, and the new Pacaya respectively. And then we use the inversion of Hermann to estimate the 1D velocity model beneath the entire volcano. So you can see, for example, in the yellow and the orange and the blue lines, you can see the 1D velocity model of old Pacaya, new Pacaya. You can see that there is no remarkable variation of velocity about new Pacaya and old Pacaya. And then we compare our result with that found of Federica Lanza using a small aperture array located in the southwest part of Pacaya in 2011. And you can see that our results were comparable to that found of Lanza. So even though we have only a few days of data, our signal to noise ratio was low, but our results were comparable to that one. So I mean, it's not a bad result. So regarding the spark here, I'm representing the comparison between the methods that we described before. You can see that all methods are comparable, are in the same range. So we use different type of methods. So we use the Menck-Engine, you use the spark, you use the Ekstrom and NA methods, but you can see that the results are comparable for different distance between stations. for example, in this case, from 400 meters to 1.5 kilometers about two stations that we did the cross correlation. So we can make some consideration about these results. So the first consideration that is that if you focus your attention of the extron method, so the dot, the green dot, this is representing and the spark, you can see that almost the increase in the frequency, they're almost the same except for the first zero crossing. So that probably is too high for being only a surface wave. So the other consideration is that we have found that this dispersion curve are higher respect to what we think in a volcano. So, and then we note that there is a flat behavior above 1.5 Earth. So these are the considerations that we have just seen. So for the similarity between the extron method and the modified spark, and except for the first zero crossing, we decided to remove the first zero crossing and fit again with a power law equation. So you can see that the dispersion curve is smoother respect to the Menke engine method, and then our fit is pretty good. So the fit between our cross correlation and the calculated Bessel function of our dispersion curve is pretty good. So for the generally high phase velocity and the pretty flat behavior by above 1.5 Earth led us to think that we are not looking at only surface wave, but probably there are also body waves to form scattering waves. So the distinction between surface wave and body waves are that surface waves are dispersive. So this frequency is correlated to the velocity is correlated to the frequency, while body waves are not. So body waves are not dispersive. So if we do the dispersion curve of a body wave, it could be like a flat line, because their velocity doesn't depend on the frequency, but depends only of the distance between stations. If we have large distance between stations, a body wave can go deeper and so can reach high velocities layers, and then it could be faster. And so we try to calculate, to make a relationship between the distance between stations and the velocity at different frequencies. So you can see you use in the left part, you use the 26 dispersion curve for the comparison between the Menke engine method and the extron method. And so you can see that there is an almost linear relationship between distance between station and velocity above 1.5 to Earth. Instead of the Honey method, so we estimated 66 dispersion curve, and you can see that there is a completely linear relationship between the velocity and the distance. And so these results led to us to think that probably we are facing not only surface waves, but we are facing the contribute of a mixture between body waves and surface wave to form scattering waves. Because why do you think this? So the reason is like that we have distance between stations that is small and is close to the Pagaia event. So we can expect that close to the Pagaia event we have rapid variation in temperature, so rapid variation in velocity. So we don't have only surface waves, we have also scattering waves. So scattering waves are waves that are reflected, that are refracted, that are converted between P and S wave. So for us, so for me, this linear relationship is takes like we have also scattering waves and not only surface wave. But keeping in mind this linear relationship between phase velocity and distance between stations, we try to find if there is any variation in velocity at Pagaia volcano. So the key concept is like we have. So surface waves are dispersive. So low frequency surface waves can go deeper, so are more sensitive to deeper velocity structure. So in simply words, low frequency surface waves can go deeper respect to high frequency surface wave. So if we do this concept, if we apply this concept, we can build a sort of 3D geometry of the entire Pacaya, of the entire volcano. So, and we can see the velocity variation of the entire volcano. So here are the six frequencies, 6 different layers find 6 different frequencies for using the Menke engine and the comparison between the Menke engine and the Ekstrom method. So you can see there is a specific pattern, but we can do some considerations. So you can see, for example, in the northwest side of the Pacaya Vein, you can see a low velocity zone. So probably at almost all frequencies. So suppose that probably there is a high temperature zone below this point. And then we have a low velocity zone probably between station 11 and station 18 at almost all frequencies except probably for the 0.5 Hertz. And then around 1 we have a almost low frequency zone in the northwest southeast trending. So my idea is like we have only a few days of data. We only 26 dispersion curve using these methods. But my idea is like this northwest southeast trending could be the evidence. I don't know, but could be the evidence for the volcanic rift zone of Pacaya. But we are not sure. Using the Heney method, you can see that there is a strong linear relationship between space velocity and distance between stations. So if you have large distance between stations, you have high velocity. So you can see that there is not a specific variation at all frequencies. So it's almost the same at all frequencies. So we don't know how to interpret it. So it's like a result, but we don't know how to interpret it because there is this strong linear relationship. Probably we are facing only body waves in this case, or scattered waves, but not surface wave. So our conclusion regarding the Benson et al. Method, so we have only a few days of data, and so the signal to noise ratio was low. So, but our result was similar, was comparable to that found by Lanza at Pacaya volcano, using the spark to apply to a small aperture array in a small portion of Pacaya in the southwest side. But regarding the spark, we have only a few days of data in this case too, but we decided to increase the signal to noise ratio, increasing the number of selected time windows used under 39. So we saw that our results are comparable using different methods, so are almost the same. So the result might be reliable. We use the idea of the modified spark applied to the extraordinary methods, and then the extraordinary methods usually were made in the frequency domain, so were made in different conditions. And we found that there are probably high phase velocities for being only surface waves. So our interpretation is that there are also body waves to form scatter waves because there was a linear relationship between phase velocity and the distances between stations. So before finishing, I want to thank a lot of people for not only for this work but for this amazing year spent in autumn. So firstly, I want to thank the coordinators of this International Dual Master in Volcanology and Geotechnique. I think that this project is one of the best projects that a university can offer. I also want to thank the Michigan Tech and the Geology Department and all students, all professors, all people that are working with dedication to help people to realize their dreams. I wish my infinite gratitude to my advisor, Greg White, for his incredible help in this work. He conveyed me his passion for seismology and for volcanoseismology, because before this year I never studied seismology, so for me he was a great person. And I want to thank you, my committee members, so Prof. Tibaldi and Simon Kahn, for accepting this important role today. And I want to thank Federica Lanza for his useful advices about seismicity of Pacaya, his incredible work of the spark in 2011. I want to thank her because she shared me with the Stromboli experience, and so I want to thank you, Fede. I want to thank also the Volcano Geophysics group, so Greg, Fede, Kyle, Hans, Sam, Max, and Monica. I know that some of you are there. To thank you because it was my first research group that I was involved in, so was very, very helpful and was very, very interesting to discuss problems, issues about Guatemalan volcanoes. I want to thank University of Milano Bicocca for this experience, and again, the Prof. Tibaldi for his useful advice, and also my family, my parents, my brother, and my grandma. Without them, I wouldn't be here. And then all my friends, the Italian one, but also in particular all friends who I met in autumn. So I felt like a family at the beginning. So it was very, very an amazing year. Thank you for all the time that I spent with you guys. Thank you very much. So thank you for attention. If you have any question, I'm glad to give you an answer. Thank you very much, guys.
I have a question for you.
Hi, yeah.
It's really something that comes from your grandmother's generation, and you made a reference early in your presentation to Cerro Grande and Cerro Chiquito.
Mm-hmm.
And I suspect that this reference comes only from the work of Al Eggers, who did his dissertation in 1972 on Pacaya. He's the only person who has ever said that they were domes. And he told me several years ago that this is not correct, that it is not a dome, and it is instead a cinder cone. And so this is that is the source of that information. You should not use that, and you should not cite it in your presentation. And this is not your fault, but it happens to many people. And I don't think it makes sense to keep saying that it is a dome if that is the source of it. If you go up there and you do work to elucidate Cerro Grande, then it's a different story. But if it really comes from Al Eggers, he himself says that this is not true.
Okay.
I wanted you to know that. And
okay, thank you.
Just because it could affect the way people think about the volcano, and if it's wrong, we shouldn't keep saying it because of this source, because he himself.
Okay.
Correct.
So our result come from the only Pacaya volcano, so only the new McKinney cone and all Pacaya. So I don't think that is coming from the Cerro Chiquito or Cerro or other domes or other cone. I don't think so. I think that our result, our data are coming from all the Pacaya event, all the Pacaya edifice.
Right. No, I understand this. I just think that, in a presentation, we shouldn't mention something that we now know is wrong.
Okay, got it. Yeah, that's sure. It's a very interesting part. Yeah. I mean, for example, the structural setting of Pacaya, I think, is very, very interesting. For future work, I think is a good thing that someone can investigate this part, because I think it's very complex, the structural setting of close to Pacaya. And so, because we have not only a compression regime, because we have only an extension regime. So I think it's very, very interesting to study this area. Not only for the volcanic behavior, but also for the structural geology. I think would be a great work, I guess.
Okay, thank you.
Thank you.
Any other questions? Wow, it's a good crowd.
Oh. Do we have a closed session as well?
Yeah.
Simone, I got a question.
Hi.
There's this new permanent seismic network that's it's going up around Pacaya with these 3 stations. I think you were part of the planning and some of that stuff, but at least you're familiar with the concept. Do you think that what extra work or what extra things could be done with those stations would those stations be useful for this technique, for one of those techniques or all of them, or what do you think? Does that have an impact on being able to explore this further?
Yeah. So if you use only the Benson et al. Analysis, so yeah, the answer is yes, because we need a lot of days of data. So we need months or years of data to increase the signal to noise ratio. So it's simply this problem. So we had only 7 days of data, so the problem was there. So for example, in the first result of the Benson et al. Analysis, which was compared with the FEDE data, the FEDE work. I think that if we have a lot of days of data, we have years of data, I think it will be great for this. I mean, for at least for the Benson analysis, also for the Spark 2, because it's the same. It's only to increase the signal to noise ratio to take in the cross correlation, to have a spike in the cross correlation. Sorry for this.
Thanks.
You're welcome.
Okay. Well, let's wrap it up. We'll have just a short, after this we'll have a short session with just the committee, okay?
Okay.
Okay.